Hello, my name is Mariah Doughman, and I am a chemistry PhD candidate at Florida International University. I will be presenting the impact of major groundwater components on the adsorption of hexavalent uranium to Hanford Formation sediment. The Hanford site is a decommissioned nuclear production complex on the Columbia River in Benton County, Washington. Waste at the site includes a number of activation products, along with uranium and the product plutonium. The waste tank farms are distributed between the 200 west and east areas at Hanford, where depth to groundwater ranges from 200 to 300 feet. This is located in the dark green area of the map, and an image of the waste tank farms is located on the right. This image is a schematic of waste leaking from the tanks, migrating through the vadose zone, entering the groundwater, and flowing towards an impact receptor, in this case being the Columbia River, a major water resource in the Pacific Northwest and a path for public exposure. Under oxidative conditions such as those present at the site, uranium is present in the hexavalent form and will complex with carbonate, making it very mobile. Divalent anionic uranyl dicarbonate complex at pH 7 to 8 is an example of a common uranium species. Consumption of uranium-contaminated waters can have toxic effects on the kidneys, bones, and livers of animals and humans. At the Hanford site, uranium was released from the waste created during reprocessing of fuel rods during plutonium production. The ongoing active remediation in the 200 area for uranium is pump and treat technology. As shown in the schematic, contaminated plumes are pumped out of the groundwater and placed through a series of sorbents such as activated carbon. Then the water is pumped back into the ground away from the plume. This technique is effective but also very expensive. Once active remediation is completed at Hanford, a transition to more passive approaches such as monitored natural attenuation is needed. This will allow us to determine if the concentrations of target contaminants such as uranium are behaving as predicted, and if mobility is reduced by natural processes. Effective monitored natural attenuation requires a thorough understanding of the contaminant immobilization processes that keep the contaminant stable and resistant to remobilization during any changes in environmental conditions or groundwater chemistry. This is a generalized cross-section through the Hanford site, and the area of interest for this study is composed of Hanford Formation sediment in this gray region. Uncontaminated sediment samples were sent from the Pacific Northwest National Laboratory, and the Hanford Formation samples were collected from Pasco, Washington, from the Tri-State Asphalt Gravel Pit. The next slides will describe the characterization of this sediment. A section of sediment was sieved into different fraction sizes, including 2 to 0.5 millimeter, 0.5 to 0.063 millimeter, 0.063 to 0.02 millimeter, and less than or equal to 0.02 millimeter. These fractions were analyzed via Bronner-Emmett-Teller method to determine the surface area of the different size fractions. The smallest fraction size of less than or equal to 0.02 millimeter had the largest surface area and will participate in the adsorption process more actively than the larger fractions. Mineralogical makeup of the sediment was conducted via X-ray powder diffraction analysis. Silicon oxide or quartz was a major mineral found in the fraction. The presence of plagioclase feldspars, phyllosilicates, and aluminum silicates were also detected. This agreed well with the elemental analysis done via scanning electron microscopy with energy dispersive spectroscopy. The major element found in each fraction was silica, but there was also a significant percentage of magnesium, aluminum, calcium, iron, and sodium detected in each fraction. Speciation modeling was conducted to establish the dominant uranium species present in the artificial groundwater solution prepared for the batch adsorption experiments. This is critical for estimating the level of adsorption that will occur and the mobility of uranium. Thermodynamic constants came from a modified Mintech thermo database. Other than uranium and water as a solvent, the basis set was composed of ions present in the artificial groundwater. The pH was set to 7.8 and assumed that the reaction was open to the atmosphere by including oxygen and carbon dioxide. Quartz was also included due to its large presence in all sediment fractions. Results of the speciation modeling indicated the dominant presence of tertiary uranium complexes, including a neutral calcium uranyl carbonate complex and a -2 calcium uranyl carbonate complex. Previous studies have found that the formation of hexavalent uranium neutral and negatively charged species will decrease uranium's ability to adsorb to sediment and will increase its mobility. Under these experimental conditions, it was also found that schwarzite is saturated depending on the uranium concentration. This means that removal of uranium from the aqueous phase in batch adsorption studies will also be due to precipitation and not just adsorption. Solid uranyl nitrate hexahydrate was used as a source of uranium at a concentration range of 9,000 to 50 micrograms per liter. These are site-relevant concentrations that were found in a 2018 Hanford site groundwater monitoring report. Sediment to artificial groundwater was set at a 1-to-1 ratio, and samples were placed on an end-over-end tube revolver as pictured on the left at 8 RPM. Samples were sacrificed to ensure a constant solid to solution ratio at the following times to establish equilibrium time: 1, 3, and 8 hours, 1, 2, 3, 4, 5, 7, and 14 days after the addition of the spiked artificial groundwater to sediment. The following graphs are of log Kd on the left and removal percentage on the right versus the initial uranium concentration in artificial groundwater onto Hanford Formation sediment. At higher initial concentrations of uranium, there is an observed decrease in log Kd and removal percentage. This is indicative of the exhaustion of available adsorption sites for uranium. Data was fit to the Langmuir, Freundlich, and linear adsorption isotherms of uranium in artificial groundwater onto Hanford Formation sediment. The Langmuir model gave the best fit with a correlation coefficient of 0.99. The maximum adsorption capacity of the sediment was determined to be 5.6 milligrams per gram. This minimal sorption is due to the tertiary uranyl complexes found in the speciation modeling. The neutral complex will have difficulty adsorbing to the sediment due to its neutral charge. The complex with the -2 charge will also have a difficult time adsorbing to the sediment due to an electrostatic repulsion with quartz, which has a point of zero charge at a pH of around 1.3 to 3.5. The presence of calcium in the artificial groundwater can also contribute to the minimal adsorption by removing available adsorption sites for uranium and by changing the surface charge on ferrohydrite species that may also be present in the sediment. Data was also fit to the pseudo-first and pseudo-second order kinetic models. The pseudo-second order gave the best fit as pictured in the table on the right. Pseudo-first and pseudo-second order models can describe adsorption kinetics well, but they cannot characterize adsorption mechanisms. However, the intraparticle diffusion model, as shown in this figure, can reveal adsorption mechanisms and identify the rate-limiting step of the reaction. Because the data does not pass through the origin, the adsorption is not governed solely by intraparticle diffusion and is instead controlled by a multi-step mechanism. The first stage is known as film diffusion. Complex uranium molecules are transported from the bulk liquid phase to the sediment's external surface through a hydrodynamic boundary layer or film. In the second stage, complex uranium molecules diffuse from the exterior of the sediment into the pores of the sediment. This is known as intraparticle diffusion. In summary, uranium speciation under site-relevant conditions is dominated by a neutral calcium uranyl carbonate complex and a calcium uranyl carbonate complex with a -2 charge. These species cause a lack of adsorption, with a maximum adsorption capacity of 5.6 milligrams per gram, and an increase in mobility for for a hexavalent uranium. The adsorption that occurs follows pseudo-second order kinetics and is controlled by a two-step mechanism: film diffusion and intraparticle diffusion. This study contributes to the technical basis required for monotiered natural attenuation at the Hanford site, which will be implemented after active remediation is complete. Future work will include the investigation of the inclusion of other contaminants to establish the true adsorption capacity of the Hanford Formation sediments. And it will also include characterization of post-treated sediment using XRD and SEM EDS analysis. I would like to acknowledge from Pacific Northwest National Laboratory, Drs. Nicola Kafoku, Hillary Emerson, James Sikoti, and Vicki Friedman. From Florida International University, I would like to thank Dr. Kevin O'Shea, Dr. Yelena Ketsenovich, Dr. Ravi Goodavali, and my lab mates. I would also like to acknowledge the DOE Fellows Program under the DOE Cooperative Agreement, with Dr. Leonel Lagos being the PI. And I would also like to thank my committee members. Thank you, and I would like to take any questions at this time.